All right, hopefully you have tried and visualized the electric field. So how do we do this? Well, we can use the same argument at every single point. I mean, for example, I could do the same argument at this point and this point and that point and that point, and so everywhere electric field line comes towards the right over here. I can do the same argument at the top or the bottom, and so you can kind of see everywhere electric field line should be towards the right, because remember, this is infinitely big line, so I can split it anywhere and I'll always get two halves. Same argument holds. Okay, won't hold for a finite line, of course, but infinitely it'll hold. So everywhere electric field lines over here will be to the right, everywhere over here it'll be to the left. So it'll look somewhat like this. Of course, now the field lines look parallel to each other, so you might think, is this a uniform field? No, it's not. It's not uniform, because if I were to come a little bit outside the screen, then in front of this, then the electric field will be away out of the screen. And if you go inside, the electric field will be again away into the screen. So let me try and show you that. It will look somewhat like this. Does that make sense? Everywhere, basically, the electric field will be pointing away from the line of charge. If I were to, kind of show you from a different angle, it will look somewhat like this. This is that same line. I've drawn some, thickness over here. Electric field is going away everywhere. Hopefully, you're able to visualize this. All right, there's another speciality to this electric field. You see, like I said, there's nothing special about point P, so whatever is the magnitude of the electric field over here, same must be the magnitude at this point at distance r, right? Because these two are almost the identical points. I mean, if you think of this as the center of this line, this point will also be the center of this line because it's infinitely big. And same will be the case over here or somewhere in front of it. So we can also understand that at any point at distance r, the electric field should be the same. Wherever you go at distance r from this line, electric field should have exactly the same magnitude. That's what we meant by symmetry. This is the speciality of this electric field. So let me just get rid of this. The next question would be, what do we do with this? Now that we know what the electric field looks like, we are now ready to apply Gauss law. And remember, Gauss law requires a closed surface. The whole idea is to calculate the flux through the closed surface, and we say that equals the total charge enclosed by the surface inside the surface divided by epsilon. That's Gauss law. So we have to first now choose a closed surface. That's our next task now. And again, no surprise, you're gonna help me do that. You're gonna choose it, and I'm gonna give you some insights of how we do that. Remember, to make sure we are able to solve this without any integral, we need to choose a surface such that electric field everywhere on that surface is going to have the same magnitude. Why? Because if the electric field has the same magnitude everywhere, then you can just remove it outside the integral, and that's when it becomes much easier to solve this integral. And that's the whole point of using Gauss's law. And so the next task would be to figure out what surface would you choose such that electric field everywhere on that surface will have the same electric field magnitude. So again, great idea to try this before I see you in the next video.